all the elements leave their mark. So when the light arrives at the Earth, it contains the complete chemical formula of the Sun.
If we take the spectrum and spread it out to fine details, and what we've done here is stack up pieces of the spectrum one on top of each other, you see all of these dark areas. The key to figuring out how much of these elements are there is the breadth and the depth of the line. How dark is the line and how broad is it?
The composition of the Sun lies in this barcode. All the thin lines are caused by tiny amounts of complex elements, metals like iron and magnesium. But there are 3 very deep broad lines, and they are all caused by an enormous amount of a single element. There's some helium and traces of heavier elements, but over 90% of the Sun is hydrogen. It's the simplest and most common element in the universe. The secrets of the Sun's power must lie in this gas. Look carefully into the night sky, and you'll see huge clouds of hydrogen floating in interstellar space. These are nebulae, and they can be hundreds of light years across. They are some of the brightest areas in the sky, lit up by the intense light of newly formed massive stars. In them, we can see stars being born. It is to areas like this that astronomers turn their telescopes when they want to study how our Sun was formed.
There she is. Okay. So now let's recenter on her.
By studying different nebulae, it's possible to piece together the stages in which stars are made. And it all starts in a cold, dark cloud, floating around waiting for something to happen.
Cold clouds like this are actually quite stable. They will sit there for a very, very long time, for thousands and in some cases millions of years before they'll actually do anything. What you need to do to get the star formation process going is you need to kick it with something. That can be an impact on the cloud from one side by a supernova blast wave. A massive star nearby has gone boom at the end of its life, and that sends out in all directions very energetic compression waves that hit the gas and compress it.
The shock waves knock the cloud out of balance, causing localized clumps of hydrogen to form. These are the seeds from which stars grow. The increased gravity of the seeds sucks in more and more hydrogen in a runaway process that lasts for 1 million years. As more hydrogen is squeezed into the clumps, the temperature rises. They are not yet producing light, but they are well on their way to becoming stars. As they grow bigger and bigger, they start to spin and throw out a disk of debris that will coalesce to form a solar system.
This kind of process is exactly the kind of process that would have formed our solar system. When we look at our solar system, all of the planets rotate around the Sun in the same direction, and they all are in the same plane, the same flat sheet around our Sun. And this is exactly a consequence of the fact that the early solar system formed out of a broad disk.
With the solar system in place, all that is left is for the young star to light up. When it happens, it is sudden and irreversible.
Ultimately, the process starts. And because it liberates so much energy with that first fusion, then the process takes off. It lights up a large area and it starts to shine on its own within a matter of minutes. It's a very quick process.
In that first burst of light, the star has begun its lifelong activity as a factory for making other chemical elements. Every atom in everything around us was made in the heart of a star, and all were made from the same starting ingredient.
The simplest element that we have is hydrogen, and it's actually the building block for all the other elements that we have.
In the heart of the sun, hydrogen nuclei, protons, are stuck together to make helium. It sounds straightforward, but it can only happen in the most extreme conditions.
In order for these protons to come together, because they're both positively charged, they don't want to come together. They've actually got to be pushed together. In order to do this, you need very high temperatures, so they're moving very fast, and you also need very, very high pressures.
The only part of the sun that is hot and dense enough is the core, an area that contains over half the star's mass in less than 2% of its volume. Here at 15 million degrees, the protons are bashed together so hard that they fuse. A helium nucleus is a tiny bit lighter than the combined mass of the 4 protons it is made from. And as Einstein tells us, it is that tiny bit of lost mass that provides the power.
Energy is equal to mass times the speed of light times the speed of light. Now, the speed of light is a very, very big number. So if we just take a small amount of mass, we get a huge amount of energy. And that's the energy which actually powers our sun.
Every second, 5 million tons of the sun is converted to pure energy. And although it has been burning for 5 billion years, it is only halfway through its supplies of hydrogen. The light produced in the core must travel over 500,000 kilometers to the surface, and it does so very slowly. The heart of the sun is so dense that the speed of light is less than 1 millimeter a second. It can take 200,000 years for the light to travel from the core to the surface. It takes just another 8 minutes to get to the Earth. This is what the power of nuclear fusion looks like from 150 million kilometers away. This is what it looks like close up. The H-bomb was man's first attempt at recreating the sun on Earth. A balloon full of hydrogen squeezed until it released its energy. In contrast to its destructive power, it's long been realized that controlled nuclear fusion could solve the world's energy problems. It has been one of the holy grails of science for half a century.
This kind of power, the H-bomb, is a man-made version of this, the sun. In 1958, Britain announced that she could produce this power in the laboratory in a machine called Zeta. There is a real prospect of unlimited energy from controlled thermonuclear fusion.
Unfortunately, it wasn't that easy.